Recent announcements of average gate fidelities exceeding 99.9% for single-qubit gates and 99% for two-qubit gates engender optimism that fault-tolerant quantum computation is now within reach. We explain that reported average fidelity can, at best, define wide bounds on the error rate of a quantum gate, which is the appropriate metric for assessing progress towards fault-tolerant quantum computing. Our conclusion is not that we are far from fault tolerance. Rather, we conclude that currently reported average fidelities are insufficient to demonstrate that fault tolerance is within reach. What is needed is information about gate performance in addition to average fidelity. The possibility of fault-tolerant quantum computing is guaranteed by the threshold theorem. The threshold theorem shows that fault tolerance is possible if the rate of error is guaranteed to fall below some threshold value. In general, determination of the rate of error requires quantum process tomography, which is often prohibitively difficult. Average gate fidelity, which is experimentally accessible, has become a common proxy for the error rate, but the average gate fidelity is not a function of error rate. Consider the case of depolarizing noise, acting on a single qubit. This induces Pauli errors. If depolarizing noise is the only source of noise, there is a simple relationship between the average fidelity and the error rate. Contrast depolarizing noise with the case of unitary errors, again on a single qubit. Such errors, if small, are far from Pauli. We demonstrate a rather different relationship between average fidelity and the error rate in this case. In general, one can place the following bounds on worst-case error rate as a function of average fidelity and gate dimension. The lower bound is known to be tight and is in fact saturated for Pauli errors such as those induced by depolarizing noise. The upper bound, however, is not known to be tight. We conjecture that it is. We demonstrate that a known upper bound to the error rate scales optimally as a function of fidelity and of gate's dimension. Furthermore, we conjecture that this bound is tight. We also demonstrate that knowledge of what we call the Pauli distance enables better bounds to be placed in principle on the error rate. Without such additional information, 99% fidelity for two-qubit gates guarantees only that the error rate is below 45%. We conclude that currently reported average fidelities are, by themselves, insufficient to claim that a fault tolerance threshold has been surpassed. Our results on the Pauli distance demonstrate that consideration of additional noise measures is required to justify such fault tolerance claims.